Okay, so now we're going to look at an example where this is kind of included in there. So you can see these are the same weights we had before and the same chalk weights as before. But if you don't want to do that as a separate line below, you can remove the tare weights right in the get-go here. So essentially what we do, we start with our weights, and then we add the negative tare weights to get our net weights. You see how that works out? So the nose waypoint minus 2.5 pounds. Here's those two. Remember I said there were two 5-pound chalks? On the previous example, I combined them because they're at the same arm. Here they are listed next to each main landing gear. And that gives us our net weight. And then the process works the same as before. So we're going to take our net weights times the arm. Oops, we add up our net weights to get our empty weight. I always forget that part. And then we multiply our net weights times our arm to get our moments. Okay. So this is exactly the same as the table we did before, just pulling those tare weights, those chalks, removing the weight of the chalks before we calculate the CG. We get our empty moment there. And then we divide our moment by our total net weight to get our CG arm location. Okay, so you see that works the same. We get the same result. It's just two different kind of paths to get there. Now where we can continue to use this, if I take that same, what we just did, and now we can track any kind of modifications, alterations, or repairs and maintenance actions that we do. And so you'll see this is the weight, the aircraft empty weight table that would be in the pilot operating handbook, and then the weight and balance table that tracks any of these changes. These would be in the pilot operating handbook or in the pilot operating handbook or the, what's the other one? Or the aircraft flight manual, thanks. And then we can track that. So say we removed a rear bench seat. This is something the engineering college used to have I think it was a 182 over in Kalamazoo that they would use for the aeronautical engineering program. They removed the bench in the back and they put in an equipment rack to have test equipment on board. They had this big long pitot tube thing sticking out of one of the wings. And then they had cameras mounted on the outside where they could do like airflow. They had cameras and basically pieces of yarn taped all or attached all over the outside of the wing so they could see airflow over the wing. And so all that equipment fed into an equipment rack where the rear seat used to be. So if we remove the rear seat, you can see here when we remove a seat, for instance, I'm going to give it a negative weight, right? We're taking the seat out, so the weight is negative. The arm, where did I get the arm for the rear bench seat on this aircraft? Where did I find that distance? Because that's the center of weight. That's the center of weight for that seat. So where did I get that from? Where did I go back to find that? There's actually two places we could probably find it. What? Not the maintenance manual. So the TCDS is going to list the location of the rear seat. What's the other one? The PO8. Remember that aircraft equipment list I showed early on yesterday? Okay, so there's the equipment list that shows the installed, the optional, the replacement equipment, that kind of thing. The different types of equipment. So that's another spot you could get this. Okay, small airplanes are in the POH. Big airplanes, it was a separate document because they said, well, there wasn't really a POH. There was the flight manual, and yeah, they didn't put all that in because frankly, our pilots didn't care about that. They had a passenger manifest where they would do it. So that listed, they could calculate passenger weight, but okay, so small airplanes, it's in the POH or the flight manual. So now we're going to install that test equipment rack. We're going to say it weighs 28 pounds, just a little aluminum rack. And it's a little further forward. Okay, 170 inches is its center of mass. Now that doesn't include any of the equipment in it necessarily. It's just an aluminum rack to be able to slide boxes into. Anytime we add or remove a box from that rack, you might have to do this process again. So we just add up our weights. Here's our updated empty weight. So you can see the plane has gotten a little bit lighter. 35, 36, 37 pounds lighter, right? Because we took out 65 pounds, added 28 pounds back in. And then we multiply, and you'll notice that the removed bench seat has a negative moment because we have a negative weight. So a negative times a positive is a negative, right? So negative 65 times 175 gives us that negative 11,375. And then our positive weight of the new rack going in times the arm of 170 gives us 4,760. And what do we do with those? What's the next step? Once we have our moments, what do we have to do with the moments? Add that whole column. So we take the 250,875 starting point. We add the negative 11,375. So we're going to essentially subtract 11,375. We're going to add 4,760. And that gives us a new moment, empty weight, empty moment of 244,260. And now we need to find the CG. How do we find the empty weight, the new updated empty weight center of gravity, the arm for the CG? The moment, 244, 260, divided by the new weight, 2413, gives us 101.23. So about 101 and a quarter, right? 101 inches. Okay, so it's moved our CG forward about just over an inch, right? And it's dropped our weight by, what did I say, 37 pounds or so. It gives us a little more room to carry. Now we'll be plugging in equipment and adding cameras and all that other stuff that, we're not going to go into every single detail. Okay, so that's how we can use this to do it. Now that could be, in this case it was a rack, but it could be we took out the cloth seat, we put in a leather seat. It could be we took out an older style NavCom and added something that had GPS along with the nav system, right, along with the NavCom. So, but where this will get used is for flight loading. So now, we have an empty weight. Now we can do a flight loading table. And this is what the crew would normally do. So they might add something that looks like this. They're going to have to add in, they'll take out their unusable fuel. Remember, our empty weight includes unusable fuel. They often have to, the crew will take out the fuel because then they're going to add fuel back in, like they know a total fuel they have on board, right? So they take out the unusable fuel, and you can see the fuel's in a slightly different location. That's what I was talking about, where a full tank versus an empty tank, the fuel CG may shift a little bit if the tank's not perfectly flat on the bottom, right? So the CG of an empty tank or a near empty tank is going to be different than a full tank. The pilot, we got a pilot flying, okay, and there's their seat location. Baggage, you can see that's quite a bit further back. And now we're going to install some test equipment in that rack as well. Add those up, gives us 2932, 2,932 for our loaded. This is now our loaded weight. Okay. The crew, the operator would have to make sure that that is below the max takeoff weight or the max ramp weight if they're planning to burn some of that fuel off. Make sure they're below max takeoff weight before they take off. But we also have to calculate a moment. So we're going to multiply each of those across. You can see the top one, the negative 18 times 110 gives us a negative moment where we're disregarding that unusable fuel and then adding back in a full fuel tank. Our pilot, baggage, and test equipment, all of those moments. We add that right-hand column together, including adding the negative is effectively a subtraction. So adding that together gives us 309,495 for a moment. And then how do we find the loaded CG? take our loaded moment and divide it by the loaded weight. You can see now it's moved back a little bit because we've got a lot of stuff behind. You know, our test rack, we've added stuff, our baggage we've put in the back. The pilot is behind the normal CG location. No, it's right near, sorry, he's right near it. The fuel's a little bit behind it. Okay. So it's moved our CG back about 5 inches, just a hair over 5 inches. Okay. And the crew would then go and look at the weight and balance envelope. I'll show those graphs in a minute to make sure that's within an acceptable range or a legal allowable range to fly the aircraft. So there's 3 methods that can be presented. Okay, we're going to look at those envelopes. How do we know if this number is in the right spot? So there's 3 methods for it. We're always going to look at the loaded aircraft weight. What's our total weight, right? And we need to make sure it's below the takeoff weight, at or below the takeoff weight. If you're right at the takeoff weight, it's a little dicey too. But they build in some cushion when the engineers figure out these loading envelopes. And then we can look at what's the CG arm. Okay, is the CG in the right spot? Or some tables or some graphs look at the moment. They don't even have you divide it. And this is what I was talking about. It could be the raw moment, like we've been working with, but it could also be divided by 100 or divided by 1,000. So you just got to pay attention to that. Keep that in mind when you're looking at that. Or it could be one that's called the percent mean aerodynamic chord, and that's typically used on swept wing. That's what we used on the airliners was MAC, mean aerodynamic chord, because that accounts for the fact that, remember, in a swept wing aircraft, that center of gravity is going to change just because of the fuel burn, and so we have to look at that. That has to be taken into account throughout the flight. So here's a loaded weight versus loaded CG versus the arm. So the airplane the airplane weight on the left, loaded airplane weight, okay? And it starts at 1,500 pounds and goes to 2,400 pounds roughly. Here are our airplane CG locations. In inches on the bottom, they do millimeters and weight, you know, if you're in the metric system. But here's our inches across the bottom. And this envelope, this trapezoid that's given here is our center of gravity limits, our CG limits. Now, this is also broken into, this is a, can't remember if this is a 172 or 182, but it's broken into what's called normal and utility category. Anyone know what the difference there is? Any of our pilots? I don't think the Cirrus has utility category, does it? No, it's just a normal category. The 172 and the 182 does, I think. Anyone know what utility category is? No. Utility category, you can see, is kind of smaller, so it's more restrictive. Utility category allows you to do minor aerobatics. You can do, what, stalls and spins in it? Yeah. So it allows you to do a little more performance flying, I guess. Can't go utility. And the only way to be in the utility category, you can see it's a lower weight and it's further forward. What kind of a loading configuration do you think would be lower weight further forward? Who would be in the airplane? Typically, to get in the utility category, it's only a pilot and a single passenger or a co-pilot. You can't have anyone sitting in the back or any baggage. That's why it's the lower weight further forward. And that's why it's also easier to recover from like a stall, because you can get the nose to point down easier, right? Because how do you recover from a stall? Full power, nose down, right? And what? Throttle forward, nose down. That's the basics I know of it, okay? So you try to power out of the stall. So you have to have that weight forward to be able to get that nose to come over, okay, or out of a spin. So utility is more restricted, but the way we had it loaded, we had that equipment rack in the back and we had baggage and all that. You can see in this example, if we have a loaded weight of 2,000 pounds and a loaded CG of 44, we would end up here. That's a legal loading, okay, for example. Here's a version of loaded weight. So the weight still is on the left side versus the loaded moment. And this is a loaded moment, and notice it's divided by 1,000. Okay, so 50,000, 55,000, 60,000, 100,000, 115,000. Okay, so remember, there's 3 zeros that would be after that. You have to divide that moment column by 1,000. That's all that means. So an example here could be a loaded weight of 2,250 pounds, moment 95 inch-pounds, divided by 1,000. You can see it falls in that normal. And this is another aircraft that has the utility category. There's a possibility, again, a little bit lower weight, a little bit forward. Loading is further forward, so you can do some more higher performance stuff with it. Okay. Or 900, it could also be 950 inch-pounds divided by 100, or it could be 95,000 inch-pounds. Right? Those all mean the same thing when we're talking about the moment. It's just they divide it to make the numbers a little bit smaller. Okay. That third one you'll see is loaded weight. So it can be loaded weight or loaded weight no fuel. Sometimes you take the fuel out depending on the aircraft. So this is a zero fuel, what's called zero fuel gross weight in this example. That means it's the weight of the passengers, the baggage, the service, the Coke cans, the magazines, the overhead stuff, you know, but we're not including fuel in here. The fuel is kind of kept separate. The idea is that as long as there's an envelope established where if the plane's loaded with other stuff, no matter how you fill the fuel, it's going to be within acceptable range. And that's how the airlines operated. We said we didn't want to have to worry about how much fuel we're carrying every time we fly the plane. Sometimes it's going to be a shorter flight. We're not going to put a lot of fuel on board. Sometimes it's going to be a longer flight. We're going to have to put a lot of fuel on board. But no matter what, we don't want to have to worry about, does the fuel load affect how many passengers we carry, where we put the passengers, what kind of baggage. So we just said, you know what, here's our zero fuel gross weight. And as long as when we calculate passengers and everything else, we're in this range, it doesn't matter how we fuel the airplane, whether it's a short hop or a long haul flight. But we do it versus our what's called percent mean aerodynamic chord. Okay, and you can see it's a little bit more complex shape. But, you know, for example, if we had a zero fuel gross weight, 46,000 pounds, which probably means the aircraft fully loaded, fuel can sometimes be upwards of 50% of the weight. It could be close to 90,000 pounds in this example, if you include the fuel. And a CG percent MAC of 40%, you can see I'm in the range there. And I just explained why fuel isn't included, because we want to be able to load the plane no matter what the length of the trip is and how much fuel we need to carry. But a lot of people wonder, what is mean aerodynamic chord? Where does this come from? So here you can see is a picture of a wing, how to find the neck. So left side here is our root and our wing tip, and you can see it swept back. Okay, remember this will contain fuel, so as we burn the fuel weight's going to move forward. But what we have to do is we measure the root length, and we add twice that to the tip. We put one root length in front and one root length behind the tip to get this full length over here. And then we measure the tip and add that to the root. One root length, or one tip length in front, one tip length behind, to get this kind of trapezoid shape. Then we draw lines across them to find the center point of the wing. This is the effectively the weight center point of the wing. And this is where if you pick the wing up, that's where it's going to balance, front to back, left to right. Okay. We measure the distance front to back of that, and that is our mean aerodynamic chord. Okay? That's the center of balance of the wing. So it's called our mean aerodynamic chord. So our CG is going to be somewhere along that length. Okay, when I start talking about percent of mean aerodynamic chord, it has to fall somewhere along this. And it can't be 100%. Let's go back to our chart. It's a lot of steps to get there. You can see my MAC is, you know, relatively between 37 and 45% of mean aerodynamic chord. So we can't have our CG across the entire wing. We only have it over a small portion of the wing. In this case, what did I say? 37 to 45, so 8%. There's an 8% range of that entire chord that we're allowed to have CG, and then it can be more restrictive too, depending on weight. So we found our mean aerodynamic chord. We've got about 8% of this line that we can play with. But what it is, it's the average length chord of the swept-back wing, and it's the distance back from the leading edge along the max. So, for instance, here, if our CG falls in this location, it's 25%. It's a quarter of the way from that leading edge to the trailing edge, from the front to the back. Here's a 50% max. So you can see that's actually too far forward in our example, right? Because it was 37 to 45%. That's too far back. So we have, too far forward, too far back. So the area our actual balance can be on the aircraft is something like that. It's that small section between my fingers, right, is where we're limited to. 75% Mac, if you're doing that, you're going to be stalling out. And that's it. 100% would be the trailing edge. 0% is the leading edge. Okay? So that is the long and short of weight and balance. So for the assignment, we'll get the assignment posted. You're going to have some examples you're going to have to do. And stop this. I don't need